So, very good morning to one and all. So, it is a nice day to talk about transducers, which is the last part of your basic electronics syllabus. So, here I am Dr. Cyril Prasanaraj, working as professor in EC department, MS Engineering College. My email ID is cyril@msec.ac.in. If at all you have any queries, please get back to me on my given email ID. So, let us continue our discussion on the process of transducers. So, these are the following contents that we have as per the prescribed syllabus in VTU. We will quickly go through the process of introduction, then we will also understand what is thermometers, we will understand what is thermistors, then we will understand what will be the working principle of linear variable differential transformer, and lastly the piezoelectric transducer. So, these are the very important transducers that have been prescribed by VTU, and we may have to understand the working principle, the construction, the applications, where these transducers are actually being used and why these transducers are actually used, and let us also understand some of the important aspects of this transducers. Before we could get into the details of transducer, let us understand one of the important parameter of any transducer is it is a measuring device. So, we have to capture the physical quantities and we have to convert those physical quantity to a measurable quantity, and that is what is the basic function of all these transducers. So, whenever we talk about transducers, and because they are involved with measurement activity, let us understand what is meant by measurement and how do we measure. Whenever we talk about measurement, there are two important aspects or technological terms that we may have to consider. They are the precision and accuracy. If at all you would like to measure certain physical quantities, or you want to measure a current or a voltage, or assume that we would like to measure any of the physical quantities, we need to understand what is meant by precision and what is meant by accuracy. Let us understand what is precision and what is accuracy is. So, here we are able to see three different graphs, and on the three different graphs we have blue colored plus, and there are black into marks, and suppose that the actual reading, actual value of physical quantity to measured is indicated by plus, that is the blue symbol there, and whenever we start reading it using a sensor, for example, assume that I am trying to read the temperature in this room, and the temperature in this room, for me it is known that it is around 27 degrees centigrade, it is known to me. Now, I try to put a sensor here like a temperature sensor to measure the temperature of this room. When I start measuring temperature of this room, okay, and you may find that the temperature is now not exactly 27, it is maybe 30 degrees centigrade sometimes, and sometimes it is giving me 32 degrees centigrade, sometimes it is giving me 26 degrees centigrade, sometimes it is giving me 40 degrees centigrade. So, what is happening? The actual temperature which I know is 27 degrees centigrade, but the sensor that I am trying to use is able to give me various other temperatures. And now we find that this measurement whatever we have done has very low precision and also low accuracy. Now, suppose if at all we try to measure using a different kind of a sensor, we replace sensor, we find that the precision sensor that we used is not precise, not accurate, we bring in a new sensor, and that new sensor is able to give us a reading like this, wherein the actual temperature is actually 27 degrees centigrade in this room, but the temperature that we have used is now able to always, whenever I try to do a measurement, maybe today I try to do a measurement, and today first hour I do a measurement, today 11 o'clock I do a measurement, today 2 o'clock I do a measurement, since the temperature in this room is going to remain constant at 27 degrees centigrade, and if I use a sensor to measure that, it is able to tell me that the temperature is always not exactly 27, but it is basically somewhere very close by, okay, it is somewhere around 30 degrees centigrade. But the sensor that I have used always gives me that it is exactly 30 degrees centigrade, but it is not indicating that the actual temperature which is going to be 27 degrees centigrade. Now, we tell that these kind of transducers or these kind of sensors are highly precise, because every time I try to do a measurement, it is always giving me a temperature of 30 degrees centigrade. The temperature sensor that I used previously is not very precise. Now, if at all you take this temperature, this sensor over here, it is able to tell us that it is very, very precise, but it is low accuracy. Reason is, the measurement what we are supposed to do is 27 degrees centigrade, but the sensor is able to give us a temperature of 30 degrees centigrade. Now, let us take the third graph. In the third graph, we find that the third graph, it is very precise, plus it is also highly accurate, because the temperature that is available in this room, which I know is 27 degrees centigrade, that sensor I am going to use to measure the temperature is also able to tell me that the temperature is exactly 27 degrees centigrade, and this measurement is being done continuously or at different intervals of time. At all intervals of time, temperature is going to remain 27 degrees centigrade. So, such kind of measurement, if at all we try to do using a transducer or sensor, we find that it is highly precise and highly accurate. So, we expect a sensor or a transducer to be highly precise and highly accurate. Let us understand two important factors here. The two important factors are, one is, we know the actual temperature of this room, and that is what is our benchmark. If at all I bring a new sensor to measure the temperature of this room, that sensor or that transducer should exactly tell me that the temperature is also 27 degrees centigrade. And if I start using this sensor multiple number of times, every time it has to give me the same amount of temperature, and that is what we call it as highly precise and highly accurate. So, we whenever we try to do a measurement, it is expected that these transducers, which are measuring devices, should be able to exhibit a very, very important property, that is, they should be precise and they should be accurate. Now, with this very brief introduction, let us get involved in understanding what is a transducer. Now, a transducer, very simply defined as a device which can convert one form of energy to another form of energy. For example, whenever I am able to speak, as I was mentioning, it is a physical quantity. I am trying to produce energy from my mouth. This is one form of energy, and we call it as acoustic signals, and it is called as acoustic energy. So, this acoustic energy, what I am trying to produce from my mouth, is now captured by a transducer, which converts the acoustic signal to an electrical signal. So, if at all I use a microphone is basically a device which is able to capture the acoustic signals and converts the acoustic energy to electrical signal, and a device that can convert one form of energy to another form of energy, we call them as transducers. So, the picture that we come across over here is a simple example for transducer. So, wherein I am able to apply my I am able to speak, and the signals are now trying to fall on the microphone. The microphone captures this energy, and it is now converting that energy to an electrical signal at this point of time, at this position. So, a microphone is now called as a transducer. Now, similarly, the output coming out of a microphone is now basically amplified by an amplifier, and we call that as a control system or maybe an electronic system. The electronic system now captures the signal coming out of a microphone, processes the data, and produces another electrical signal that is available at the output of the amplifier. Now, the amplifier over here, which is able to produce the electrical signal, is fed into a loudspeaker, which further converts the electrical signal back to acoustic signals. So, a loudspeaker or a speaker, it basically is a device which is able to convert electrical signal back to acoustic signals. So, this is also called as a transducer. This is also called as a transducer, but in general, both of them are being called as what? Transducers. Now, to differentiate or to understand the difference here, a microphone is a device that is able to capture what? Physical quantity, convert that into an electrical signal. We call this specifically as sensor. So, let us understand, a sensor is also a transducer, but a sensor is a device that converts your physical quantity like speech or acoustic signals to an electrical signal, and that is why we call that as sensor. And sensor are always at the front end, or we also call them as input devices. Now, let us understand what does actuator does. The loudspeaker, which is able to take in electrical signal and converts that back to physical quantity because of the vibration that are being created, we call this as what? Actuators. So, the actuators are also a transducer, but the purpose of an actuator is they convert electrical signal back to physical quantities. So combination of a sensor and an actuator, okay, we can both together, we can call them as what? Transducers. Okay, but sensors are available at the input side and actuators are available at the output side. And in general, a transducer is a device which converts one form of energy to another form of energy. So that is the basic definition of your transducers. Let us understand what are the applications where these transducers or sensors or actuators play a very important role. Okay, so let me show a small video pertaining to automotive applications, wherein we are able to see that all the cars today that we run, okay, you are maybe you have a Benz car, or you have a Tata Indica car, or you have a Scorpio car, or you may have any kind of a car. Almost 40% of this car, okay, is basically from made up of electronics. And in this 40%, there are large number of sensors and actuators which are actually being used in this automotive. Now let us understand, okay, by watching a small video, what is the role played by a sensor or an actuator or in general a transducer in an automotive application. By watching this video, we will understand why sensors and actuators are very important for our day-to-day activities. Let me run this video and show you what is the role played by these sensors. Yes. So let us talk about the sensor part. So I am trying to just show you a small video which tells you what is a sensor or an actuator trying to do in an automotive. Okay. So we are trying to see here a smart guy like me or you driving a car. So we are able to see the animations of the car.
For grip. If this happens, the wheels can lock up, causing the vehicle to skid.
Okay. So there is a guy who is driving a car, and now we are now trying to understand what is the role of a sensor or a transducer in this car. The driver is now trying to drive the car on a road and is able to turn the steering, plus is able to apply brakes, apply the accelerator, and is able to move in a straight road, and then is trying to move, take a vehicle at a constant speed. Let us see what are the challenges.
Control. By preventing this lockup, the vehicle stops sooner and remains under the driver's control. The anti-lock braking system, or ABS, provides this assistance. So how does it work? Sensors on each wheel.
Let me stop here. So as the driver is trying to drive the car, there are sensors that are mounted on the wheels, not really on the wheels, but on the shaft of the wheel. And these wheels, the speed at which these wheels are able to rotate, there is sensor that is available to capture and understand what will be the speed of this wheel, how many revolutions per rotations per minute. So the speed at which these wheels are able to rotate are captured by a sensor to tell that, okay, the rotational energy, the speed at which the wheels are able to rotate, okay, the translation activity, that is rotational activity, is captured by a sensor, and then it is able to tell us in terms of some number that the speed is around 10 rpm or it is running at 60 kilometers per hour. Okay. Now let us understand what can we do with this.
Constantly measure their rotational speed. The ABS control module samples this data continually, comparing the rotational speed of each wheel. If one or more wheels is rotating slower than the others, a condition that will bring the wheel to lock, the system takes action. It instructs the brake master cylinder.
Okay. So let me stop here. See, what is happening is, as we keep driving the car, okay, we know that there are brake cylinders. As you apply the brake, these brake cylinders jam, and then the wheel gets locked, and the speed of the wheel gets reduced. Assume that we would like to stop the car. So to stop the car, we apply the brake. The brake will now try to initiate the brake cylinders. The brake cylinders will lock the car. So as the car is moving at a very high speed, suddenly you apply a brake. What would happen is, because of the speed at which the car is traveling and the brakes are basically applied very fast, there are possibilities that the car may topple. So to ensure that the car is moving at a stable condition and it is not going to topple, we have a concept called anti-lock braking system. Okay? See, the anti-lock braking system is a very important technology. It's a very innovative technology available in the car. So as you keep driving your car at a very high speed, suddenly some obstacle comes in front of the car and you want to avoid the obstacle and you apply the brake very fast. When you apply the brake, the sensors available in the car will now understand at what speed your car is trying to move. Then it will also understand why the brake has been applied, what is the amount of pressure you have applied on the brake. Depending upon these two, it will ensure that there is a control system available in the car which will not immediately ask the car to stop. There is some action basically being done to ensure that the car is now, even after applying a sudden brake, it is not going to topple, but there will be a smooth transition occurring in the car. Let us watch this video and understand
to
what is role
direct
played
brake
by
force
sensors.
away from the locking wheel, so it releases and regains traction. As the wheel begins to turn again, braking force is momentarily reapplied. This process is repeated up to 20 times a second and causes the characteristic pulsing feel through the brake pedal. As a result, the driver's intended brake force is applied without locking up and skidding, allowing the driver to maintain steering control while braking, meaning that stopping distances may also be reduced. The vehicle on the left has ABS.
Now let us understand, there are two cars. One car which is having anti-lock braking system, the other car which is not having an anti-lock braking system. So anti-lock braking system is a technology that is available on the car which is integrated with all the sensors, so that there is a smooth transition happening on the car. Okay?
The vehicle on the right does not. Both vehicles are travelling at 100 kilometers per hour. Let's simulate an emergency braking situation and see what happens. Both drivers apply their brakes at the same time and with the same force. But the vehicle with ABS maintains control while braking and is able to steer around the obstacle. ABS helps the driver avoid accidents by preventing lockup and loss of traction. This allows the driver to maintain steering control during heavy braking and may help to reduce stopping distance.
See, the video that we could really see was to just illustrate the applications of transducers. See, whenever an obstacle comes in front of a car, the car is traveling at a very high speed. Now, whenever the driver applies the brake, a sensor or a transducer determines the speed at which the car is traveling. It will also understand what is the force that is applied to stop the car. By calculating these two, if your car doesn't have an anti-lock braking system, you would have just gone and hit the obstacle. But because there is a system available there which is able to take data from the sensors, it is now able to give a stability control to your system car, so that you will be able to autonomously ensure that you don't avoid the hit the obstacles. You are able to avoid the obstacles, and that is the advantage of having sensors and actuators in an automotive. So if at all you see, there are more than 40% of electronics, okay, which is available on a car. So sensors and actuators play a very important role in our day-to-day activities. Now let us understand what are these transducers, or what are the sensors, what are the actuators pertaining to four major categories of sensors and actuators. Yes, let us first of all define, okay, what a sensor is. A transducer can mean a sensor, actuator, or a transducer can be part of a sensor can be part of a transducer. That means transducer is as a whole, we call it as a transducer. Sensor and actuators are part of your transducers. So a device that can convert physical quantities to an electrical signal, we call them as specifically sensors. A device that can convert electrical signal back to physical quantity, we call them as actuators, but both of them are part of a sensor. So in general, we define a sensor is a device which can convert one form of energy to another form of energy, and that is what we call it as a sensor. Now let us take a simple example. The mercury thermometer. Suppose we fall sick, so the doctor or a nurse comes and inserts a thermometer into, puts a thermometer into our hand. So we find that after some time the mercury level in the thermometer starts rising. indicating the amount of temperature that a person has. So what is happening here is the mercury is a liquid that is going to react. Okay, it is going to change its parameter whenever there is a more amount of temperature. As the temperature increases, the mercury slowly starts rising. So what is happening here? We are now able to find that the temperature changes the property of the mercury to rise in a given cylinder, and that is what we know. We are now able to calibrate it and understand how much of temperature the guy is actually having, and that is what is a function of a sensor or a transducer. Okay? Yes. The transducers can be mechanical, electrical, magnetic, optical, chemical, acoustic, thermal, nuclear, or a combination of all of them. So the physical quantities that are available on our earth, okay, the physical quantities that we come across can be mechanical. Mechanical is if I apply a pressure, okay, if I apply a sound, okay, that is mechanical. Electrical is, suppose if at all I want to identify how much of current actually is basically existing in a given region. For example, the current that is flowing through a conductor. The magnetic basically is, suppose if at all I would like to know if at all there is radiation, how much of magnetic field is available in this entire room. Or optical, what will be the amount of light intensity that is going to fall on my face. Chemical, suppose there is some amount of hazard happening, there is a leakage of hazardous gases, I would like to know what is the amount of chemical that is available there. Acoustic, so whatever I am able to speak acoustic. I also would like to know if at all I switch on the light, how much of thermal energy is basically being created. So there are multiple factors, okay, that are available, and all these factors are called as physical quantities. Okay. So these physical quantities can be measured, and that is where you come across a transducer. Mostly quantities to be measured are non-electrical, and these are temperature, pressure, displacement, humidity, fluid flow, speed. So the non-electrical quantities are like your temperature, pressure, the displacement, the amount of humidity available in this room, the rate at which the fluid is flowing in in your body, the speed, all these are non-electrical parameters. Okay? Quantities such as current, voltage, resistance, inductance and capacitance are all electrical parameters. So you can also capture the non-electrical parameters, you can also capture the electrical parameters using a transducer. You can measure them. Okay? Yes. Suppose if at all you use a transducer, okay? The transducer, as I was mentioning, should be very rugged. Okay, rugged, what I mean is it should be able to withstand overload, and some safety element should be provided for overload protection. That means if at all I am trying to measure the current that is flowing in a conductor, okay, and the current that can flow through a conductor is maximum of 10 amps of current. If I try to put a transducer there and I want to measure the current over there, okay, suppose by chance instead of 10 amps of current, the current that is flowing through that transducer, to wire goes to 20 amps. Your sensor or transducer or your system should be able to withstand that amount of overload. So that is the meaning of ruggedness. Linearity basically is, suppose I take a transducer and try to understand what will be the amount of current today. Current flowing through that is 10 amps. Tomorrow, I again come back, use same transducer to measure the current. It should again tell that the current is 10 amps. So it should be very linear. It should not exhibit non-linear behavior. Plus, it should be repeatable. Repeatable is, if I manufacture a sensor today, it is going to be available for next 10 years. So even if I start using it for first year, second year, third year, if I use it for 10 more years, it should always give me the same amount of reading. That is what we call as repeatability. Then, if at all I use a transducer, okay, and I try to measure a signal physical quantity, it should be able to produce high output signal quality. What I mean by that is, if at all there is a temperature changes occurring there, and I am trying to measure that using a transducer, if ever there is a temperature change, the output of your transducer should be able to tell me, yes, it should be millivolts or at least some amount of volts. So it should give me that, okay, it is giving me the output in terms of voltage. It should not basically give me the signal in terms of noise. So it should be reliable and stable. So as we have seen that video, okay, assume that your car is moving at a very high speed, yeah, and then you are able to measure the speed of the car. So you are able to put a sensor over there, and the sensor is able to now tell that, okay, this car is moving at 60 km per hour. So we are able to know precisely understand that, yes, the sensor is reliable. It is able to tell me that the car is really moving at 60 km per hour. So that is what reliability is. It should also have very good dynamic response, and now it is again a function of time. So, excuse me. These are some of the very important parameters, okay, that are expected from a transducer, right? Okay. Now let us understand how do we classify transducers. Okay. Transducers can be classified in various ways, such as on the basis of electrical principles involved, methods of application, methods of energy conversion, nature of output signal. So depending upon the basis of electrical principles and methods at which they are going to be used, and the methods of energy conversion and the way they are able to produce an output, transducers can be classified into multiple categories. Let us understand one of the important category here. Okay, classifications of transducers. You can classify transducers as primary and secondary transducers. Okay, what is this? Okay, what is meant by primary transducer and what is meant by secondary transducer? Okay, transducers on the basis of methods of applications may be classified into primary and secondary transducers. When the input signal is directly sensed by the transducer and physical phenomena is converted into an electrical form directly, then such transducer is called as primary transducer. Okay, what I mean here is, suppose I take a microphone. Okay, I am able to capture the speech. So the signal falling on the microphone converts. Okay, the variations are available here, converts that into an electrical signal. We call them as primary transducers. Okay. Another example is a thermistor. Okay, used for measurement of temperature fall in this category. The thermistor senses the temperature directly and causes change in resistance. So what happens is, assume that I have a conductor here, and whenever the temperature of the room changes, the property of the conductor, that is the resistance of the conductor, keeps changing. So the temperature directly influences the resistance change on the conductor, and that is what we call them as primary transducers. So let us define what is primary transducer. Primary transducer is any change in physical quantity if it can influence the change in the electrical parameter, or if it can directly change the energy, that is what we call them as primary transducers. Okay. Next category is secondary transducers. Let me take a simple example. Okay. In case of pressure measurement, assume that you want to understand how much of pressure is existing. We have a very simple tube called the Bourdon tube. Okay. So in a Bourdon tube, what happens basically is, okay, it's basically having some amount of liquid here, so which converts pressure first into displacement. So what happens whenever you try to take a Bourdon tube and then there is amount of pressure applied? So what happens, the pressure that is going to be applied on the Bourdon tube, the displacement of the liquid happens. Okay, the liquid can change, the height of the liquid can keep changing. Now this displacement is converted into an output voltage by an LVDT. Okay, now what happens, you are not able to directly convert the change in pressure to electrical signal. We are trying to convert pressure change to displacement, displacement to electrical signal, and that kind of devices we call them as secondary transducers. Okay. Most of them would be like a secondary transducer. So wherein what happens, the physical quantity is now captured by the transducer, converts that into displacement, displacement is converted to an electrical signal, and that is what is a secondary transducer is. Okay. So there are two kinds of transducers, one is primary, the other one is secondary. In a primary transducer, what happens, the signal or the physical quantity, whatever is going to fall on the system or the transducer, also gives rise to a single change. And what happens, a Bourdon tube, we can call it as a primary transducer. The output of a Bourdon tube, which is a displacement, is further captured and converted to an electrical signal. So the Bourdon tube and LVDT both combined together, we call them as secondary transducer. So we can classify transducer as primary and secondary. Yes. We can also classify transducers as active and passive transducers. What is active and passive transducers? Okay. So this classification is based upon the method of energy conversion. Okay. Self-generating type transducers, that is transducers which develop their output, the form of electrical voltage or current without any auxiliary source, are called as active transducers. What I mean here is, suppose you are able to have a transducer there, you are able to apply a voltage or you are able to apply a pressure, that pressure is converted to an electrical signal. So what is happening here? The pressure whatever we apply is now directly converted to an electrical signal, and such transducers are called as active transducers. Why are they called as active transducers? Because we don't need an external source to generate the voltage. The voltage that is available at the output of a transducer is directly generated because of the pressure that is being applied. So because there is no any external voltage source that is required, we call this as what? Active transducers. Okay, now let us see what is a passive transducer. Okay, transducers in which electrical parameters like resistance, inductance or capacitance change with change in input signal are called as passive transducers. So what happens in a passive transducer? The physical quantities that are going to be measured, okay, or if at all they need to convert the physical quantity to an electrical signal, you need an external electrical source. So if at all you bring in an external electrical source to convert the physical quantity to an electrical signal, we call them as passive transducers. So resistors, inductance and capacitance are all basically falls under the category of passive transducers, because if I take a resistor, the pressure may change. The pressure, if it is applied, resistance may change. But if at all I want to convert the resistance to voltage, I need an extra voltage source, because the resistance cannot generate a voltage. So that is why we call them as passive transducers. So let us understand the classification with respect to active and passive. In an active transducer, what happens? Whenever a physical quantity is to be measured, if it is applied across a transducer, so if I apply a physical quantity across a transducer, it will generate a voltage on its own. So such devices are called as active transducers. Okay, what is a passive transducer? In a passive transducer, what happens is, if at all I take a transducer here and I apply a physical quantity, okay, if at all this transducer has to convert that into voltage, you require an external voltage source or you require an external current source. Such devices are called as passive transducers. So we are able to now classify transducers into two different categories, active and passive. Earlier we were able to see transducers classified as what? Primary and secondary. Yes. Transducers can also be classified as analog and digital transducers. Now let us understand what is meant by analog transducer and what is meant by digital transducer. Okay, with respect to the example that we could see, the animations or the video that we could see, okay, whenever the wheel rotates, we now have a sensor which is able to measure the movement of the gears. Now, whenever the sensor is placed close to the wheel, as the wheel starts rotating, the sensor now starts measuring the gears. And for every gear coming nearer to the sensor, whenever the gear comes nearer to the sensor, okay, a pulse is generated. And the gear moves off, the pulse is 0. Whenever again the gear comes to the sensor, the pulse is generated. So if you see here, a sensor or a transducer is able to now convert the movement here, which is basically a physical quantity, to a pulse like this. Since it is pulse, and in the pulse you find that there are only two voltage extremes, one is 0, the other one is 1. Because there are two voltage extremes 0 and 1, we call this as digital data. So whenever a sensor or a transducer converts the physical quantity to two voltage levels, we call that as digital transducer. Now if at all you try to take a transducer or a sensor which is now not able to convert into 0 or 1, but whenever the gear system keeps changing, if it is able to change the voltage like this, okay, if the voltage is like this, we call that system as analog transducers. See, the first case was like this, it is able to give us the pulses, so it is either 1 or 0. But what happens in a transducer wherein the signal is going to change slowly and is able to vary, and that device or that transducer, we call them as analog transducer. So this is another classification of your transducers, right? Okay. Yeah. So let us categorize the or let us classify transducers. Transducers can be classified into three different categories. One is primary and secondary transducers. Second kind of classification is a transducer can be active or passive. Third classification is a transducer can be analog or digital. Apart from that, there are many other classifications, but these are the three major basic classifications of transducers. One is primary, secondary. Second one is active, passive. Third one is analog and digital. Okay. Now, again there are various types of transducers that are available in the market, okay, on the literature also reports various types of transducers. Suppose if at all you want to measure the light intensity, okay, assume that the amount of light that is falling on me, I want to measure that, or the amount of light that a sun is able to give us. If at all you want to measure the light, which is again a physical quantity, there are multiple light sensors available, okay. For example, it could be light dependent resistor called as LDR. So what I do is I take a resistor there, and whenever the light falls on the resistance now changes, and we call that as light dependent resistor. Then we have photodiode. Photodiode is, I have a diode now. Whenever light falls on the diode, the amount of current that can flow through the diode also changes. We call them as photodiodes. Plus phototransistors. Instead of a diode, I can replace it with a transistor. So what happens? Again, on the base of the transistor, light falls on it. Again, it will lead to some amount of current, and we call them as phototransistors. Solar cell. Here, it's a very interesting thing. What is happening? The light is falling on this cell, that is solar cell, which is now converting that to electrical current. Okay? So that is what a solar cell is, right? So the output devices are, okay, like I can take a light and lamp, LEDs, displays, and fiber optics. So here what is happening? The sensor is LDR, it can be photodiode, it can be phototransistor, but if at all I want to convert light, okay, if at all I want to convert, okay, electrical signal back to light, I need to use an actuator. What are the actuators now? A light is an actuator wherein you try to apply 230 volts of current, it is able to, or 230 volts of voltage, it is able to give you light. So that is again an actuator, okay, or LED. I try to apply some amount of voltage, if the voltage is more than some 2.2 volts, it is able to glow, and that is again an LED. Okay, I can also have fiber optics wherein I can convert your electrical signal to optics. So a combination of sensor and an actuator, all of them are basically called as a transducers, right? Suppose if at all you want to measure temperature, excuse me, yeah, if the temperature is measured, we have devices like thermocouples, thermistors, thermostats, or RTDs. So now these devices are able to measure temperature and convert the temperature to an electrical signal. So that is why we call them as sensors. If at all you want to change the temperature in a room, so we have heaters. So what is an heater now? Okay, so whenever I apply voltage or a current, okay, it will start heating up. So the temperature of the room would change. Or a fan, if I assume that the room is very hot, I switch on the fan starts rotating, the room gets cooled. So again, an electrical signal is now converted to a rotational moment, so that the fan rotates and the room is getting cooled, and that is what we call them as actuators. Okay. Similarly, if at all you want to measure the force, okay, or pressure, suppose I'm that to bang the table, what is the amount of force that is exerted? So we have devices like strain gauges, pressure switches, load cells, and again I want to generate pressure, I want to create vibrations. Again, that is an actuator there. So I want to know the position. Okay, so I assume that your circle is moving around. I want to know where the position is, or I assume that I am trying to move around. I want to know the position. You have sensors like potentiometers, encoders, opto switches, LVDTs. Similarly, you want to change the movement. Assume that I want to change the table. I want to move the table here. I can basically have motors, solenoids, and panels. Similarly, you have speed measurement done. You have sound measurements done. Again, we have sensors and we have actuators, and a combination of all of these, we will call them as what? Transducers. Okay. Now let us take up the first important transducer, that is how do we measure temperature. So to measure temperature, we have a transducer called temperature measurement, or we call it as, okay, so what you see here is a simple picture of a device that is used in an automotive to measure the temperature. Okay, yes. So how do we measure temperature? So we call them as temperature sensors. Okay, so temperatures can be measured using 2 or 3 important factors. One is thermoelectric sensor, thermoresistive sensor, and semiconductor junction sensors. So if at all you want to measure temperature, there are 3 ways to measure temperature. Okay, the first property is thermoelectric, thermoresistive, semiconductor junction sensors. Now what is thermoelectric? Thermoelectric is, the first term tells that it is thermo, that is temperature. Second term tells that it is electric now. So what is happening? This falls under a category of primary sensor, because we don't need an external source. Okay, so whenever the temperature is applied, it will directly convert that to an electrical current. That is why we call them as what? Thermoelectric. And in this thermoelectric, we have concepts called thermocouples and thermopiles. Okay. Now, thermoresistive. In thermoresistive, what happens? The temperature that is applied on the resistor, the resistance keeps changing. Okay, and we call them as what? Thermoresistive. It could be either a sensor or it could be either an actuator. Okay. So, conductor based sensors and actuators, we call them as simply RTDs, that is resistive temperature detectors. Okay. Now, it could also be semiconductor based sensors, or we call them as thermistors or diodes, or we can also use semiconductor junction sensors. So, to measure temperature, there are various aspects available. Let us discuss one by one. Okay. Thermoresistive sensors. So, let us take the first category called thermoresistive sensor. In thermoresistive sensor, there are two basic types. One is resistive temperature detector, second one is thermistors. So, we will discuss these two in detail. Okay. One is resistive temperature detector and the second one is thermistors. Okay. Now, what is this RTD, which is a very popular term called as RTD? This RTD can be realized using a metal wire, can be realized using a thin film, or it can also be silicon based. So, what is a resistor RTD now? RTD is basically is a sensor or a transducer which is used to measure temperature. Now, this RTD can be constructed using simple metal wire. Maybe I can use a copper wire, or I can use an aluminum, or I can use a gold. So, if I use this aluminum or copper or gold, okay, they are all having some amount of resistance, and these resistance actually they change. For example, whenever there is a temperature change in the room, I try to take a gold here. Okay, assume that I take a gold here, and this gold is actually now exhibiting 10 ohms of resistance. Now, as the room temperature starts increasing, and if at all I measure the temperature of the gold now, it would increase from 10 ohms. Okay, it can become 12 ohms, and that is how we measure the temperature. So, temperature is measured by noting down the resistance that is going to change in the metal, and we call them as metal wires. It can also be thin film. So, I can take a very thin film, I can put on a substrate. Now, what happens is, whenever the temperature change occurs, the thin film property change. The resistance of the thin film may also change, and again we call them as resistive temperature detectors. Similarly, instead of thin film, I can use silicon. Okay, so silicon or germanium I can use. Usually silicon is usually used. So, if I take silicon, fabricate the silicon on a substrate, the temperature of the silicon would change whenever the temperature varies in a room, and that is how you can measure the resistance. So, what happens? The current flowing through a silicon or the resistance of a thin film or the resistance of a metal wire can change depending upon the amount of temperature available, and we call them as what? Resistive temperature detectors. Okay. Now, thermistors, another very interesting part here, wherein the thermal changes the resistance. Now, this thermistors, what happens here is, okay, it can be negative temperature coefficient or it could be positive temperature coefficient. So, what is negative temperature coefficient now, or what is positive temperature coefficient? So, whenever the temperature increases, if the resistance also increases, which is called as positive temperature coefficient. If the resistance is going to increase and temperature is going to if the temperature is going to increase and the resistance is going to reduce, we call that as what? Positive, negative temperature coefficient. So, these are all the various categories of transducers that are available to measure temperature. Okay, let us understand the thermoresistive effect. Okay, so what you see in the picture here is, we are able to see a device, a small conductor. Okay, imagine that this is a copper or maybe aluminum, or it can be some kind of a conductor over here. Okay, now this conductor basically has three important parameters. What are the three important parameters now? One is the area of cross section. Okay, this is the area of cross section, and we denote it as S, which is equal to the length multiplied by the thickness. Okay, the breadth of it multiplied by thickness. So, this width multiplied by the thickness will give you the area of this section. Now, this conductor is having a length of L. So, let us for example take assume that your conductor, it's a square or a rectangle here. So, it has an area of cross section plus it has some amount of length. So, this S and L plus it also has a parameter called the conductivity, that is sigma. This conductivity sigma is again a parameter that defines the material property of the conductor. So, if you have a conductor having a cross section of S, length L and a conductivity denoted by sigma, we can now calculate what will be the amount of resistance of this conductor. Okay, the resistance offered by the conductor R is now equal to L by sigma S. So a very interesting formula that we come across. Okay, let me illustrate it. We have a conductor now. This is the conductor that is available here. Now this conductor, if at all I want to calculate the amount of resistance offered by the conductor, the formula basically given is R is equal to L by sigma S. It's a very important formula. You have to remember this formula if you are an engineer. Okay. Now resistance offered by a conductor is given by length of the conductor divided by sigma conductivity and S multiplied by S, where S stands for the area of cross section. Now if at all I change the length, okay, increase the length of this conductor, what will happen now? Resistance also increases. If at all I change this surface here, instead of having a very big surface, I reduce it, what happens now? If I reduce it, resistance increases. So the resistance of this device or the conductor changes because of L and S. Okay. Now let us not change L and S. We will assume that the conductor that we are taking into consideration has a fixed length and a fixed area of cross section. Now let us see what is going to change the resistance now. Okay, the resistance can be now changed because of the following factor. Yes, we know that the conductivity of a material is given by a formula which is sigma naught by 1 plus alpha into T minus T naught. Let us understand what is the sigma naught, what is alpha, what is T and what is T naught. So the conductivity here, the conductivity sigma is given by a formula which is this. The formula states that the conductivity is now, it is not a constant but it is going to be a variable quantity, and it is given by sigma is equal to sigma naught, okay, divided by 1 plus alpha into T minus T naught. What is sigma naught, what is alpha, what is T minus T naught, we will discuss. Okay. Now substituting this formula back into this equation, we find now the R of the resistance of the device is now L by sigma naught into S into 1 plus alpha into T minus T naught. So earlier the equation was, what was the equation now? The equation was R is equal to L by sigma into S. Now because the sigma, the conductivity now has a different parameter involved in it, if you substitute now this sigma into your equation, R of T is now equal to L by sigma naught S into 1 plus alpha into T minus T naught. So if you see here, the resistance of a device that we had considered is now not only dependent upon the length and not only dependent upon S, but also depends upon temperature T. Okay, this T naught, alpha and sigma naught are constants for the device. T naught is the temperature. Okay, now what is the temperature at normal? They assume that it is a normal room temperature, and what is temperature that is going to change? Okay, from normal temperature, if the temperature changes to T naught, from T naught, if it changes to T. Okay, so the change is now multiplied by factor of alpha, and then it is again added with 1, and then you are multiplying it again with some constant called L by sigma naught S. So the resistance that we were assuming to be remaining constant is now basically a resistance which is entirely dependent upon temperature. So there is a direct relationship between temperature and resistance. So as temperature increases, resistance also increases. So that is what we call as thermoresistive device. Okay, let us revisit what is this thermoresistive device. In a thermoresistive device, what happens basically is, okay, the temperature is going to change, and this temperature affects the resistance. Because the temperature is going to change the resistance, we call it as thermoresistive device. Okay, now the formula for thermoresistive device is R of T is equal to L by sigma naught S into 1 plus alpha into T minus T naught, where alpha, sigma naught, S and L are constants. Okay. Alpha is now called as temperature coefficient of resistance. Okay, so that is again TCR. Yeah. Let us see how does this RTD work? Okay, so what happens in an RTD? So in an RTD, what happens basically is, okay, we have now taken a conductor, assume that it could be copper, it could be aluminum, it could be anything, and we have now fixed the geometry of this conductor, a piece of material. We have taken the piece of material. So let me take for example, sorry, okay, this is my piece of material. So I have taken this as the conductor. So now I decided what is area of cross section. I know the area of cross section, I know the length of this, and I know the thickness of this. Everything is now fixed. Now this copper, if I take, has sigma naught as 5.9 10 power 7, okay, and the alpha TCR is 0.00039 degree per centigrade at T naught equal to 20 degrees centigrade. Now assuming that the wire has a length of 0.1 mm square, length of 1 meter, okay, now at T naught equal to 20 degrees centigrade, the resistance offered by that is going to be around 0.017 ohms. So the resistance offered by a copper with a length of 1 meter and, okay, cross section area of 0.1 mm square. So it may be a thin wire which is used in our house, okay, and if it's having length of 1 meter, the resistance offered by that copper wire is going to be 0.017 ohms. At what temperature now? At a temperature of 20 degrees. Now if the temperature changes, okay, if the temperature changes by 1 degree, okay, from 20 degrees, if the temperature changes by 1 degree, the temperature now is said to be how much now? 21 degrees. So what happens? The temperature which was 20 degrees has now changed to 21 degrees. By substituting 21 here and 20 here, we find that the resistance of the device changes to 6.6 into 10 power minus 5 ohms per degree centigrade. So what happens is, because sigma naught, alpha, all of them are constant and they are known to us, plus the area of cross section plus length, all of them are known to us, what happens is, whenever the temperature of the copper wire changes by 1 degree, the resistance of the device changes by 6.61 into 10 power minus 5 ohms per degree centigrade, and that is the significance of, okay, your resistance temperature detectors. So now let us see how are we going to use this to measure temperature. Okay? So what is happening here? We have taken a device called as a resistor or a wire. Okay, this wire is now used to measure the amount of temperature that is going to change in this particular room. We also know that for a wire with these parameters, per degree change in temperature, the resistance changes by 6.61 into 10 power minus 5 ohms. Okay, now let us take this wire and include it into a device like this. So we are now taking a wire, and what we have done is we are trying to put it into a circuit like this. So what is the circuit now? This circuit is, there is a resistor R1 and resistor R2. There are two resistors, R1 and R2. R1 is a fixed resistance, R2 is, okay, the resistance that is now being used as sensor. So what we have done, we have taken the sensor and then we have put it as a resistor. We are making it as a resistor now, and then we are trying to measure the voltage across this resistor, and we are applying a voltage across these two resistors. So what kind of sensor is this now? What kind of transducer is this now? This is called as secondary transducer. Why is this called a secondary transducer now? Because whenever temperature changes occur, the resistance first changes. The resistance of this device changes because of change in temperature by a factor of alpha T minus T naught. So what happens? The resistance of this device changes with regard to change in temperature. So what is happening? This transducer is now converting your temperature to resistance. Okay. So this is now called as primary transducer. If I introduce this into the circuit and apply a voltage across this, we now convert the resistance into a voltage, and we call that as secondary transducer. Now let us discuss this. So what is happening? Let us take a break and come back. Thank you.